In the last video, we saw the concept of percentage composition and mass percent. So let's do a quick recap of that, and afterwards we'll do some practice problems related to those concepts. So we know that when you look at a chemical formula, you get a lot of important information about the compound. If we analyze the pairs of compounds below, we'll notice that they're very similar in terms of the elements that they're made up of. For example, here they're both hydrogen and oxygen, but they will differ in the number of each atom that makes them up, and that gives them different properties. So water, for example, is very stable. You can store it for long periods of time. You can drink it. Whereas hydrogen peroxide is more unstable. It's more reactive. It breaks down if you leave it exposed to light. If you don't keep it in cool temperatures, it breaks down pretty quickly. And that main difference is really because of that extra oxygen that the hydrogen peroxide has, which the water does not. And then the same thing can be said about carbon monoxide versus carbon dioxide. They're very similar in their composition, but you have one extra oxygen here compared to here. And so carbon monoxide is colorless and odorless, just like carbon dioxide, but they have different properties overall. Carbon monoxide is toxic, and it can lead to death if you inhale it, whereas carbon dioxide is not really toxic like that. It can lead to severe problems if there's an abundance of it around, but it's something you breathe out and you're not really considering it in the most severe cases like you would be carbon monoxide. And so what we saw is the concept of law of definite proportions, where we basically said that the elements in the compounds are always present in the same proportions by mass, no matter how large or small the sample. Oxygen, so in water, oxygen will always be 88% of the mass, and hydrogen will always be about 12% of the mass. And what we just described there is what's called a percentage composition. It's the percentage by mass of each element in a compound. We basically say that, okay, to describe the percentage composition of water, I would say that the mass percent of oxygen is 88%, and the mass percent of hydrogen is 12%. And when I say mass percent, it just means the mass of an element in a compound expressed as a percentage of the overall mass of the compound, the total mass of the compound. So basically, what percentage is this element? What percentage is this other element in the compound? So there's a few different ways you can calculate mass percent. You can do that from data, that's mass data, or from a formula. And we'll come back to this example over here in just a minute. I want to go and further define the percentage composition. So remember, if I say I want the percentage composition of a compound, what that means is tell me the mass percent of each element in that compound. And then they should add up to 100%, because that's the percentage of all the elements in the compound. And it's always constant. It doesn't matter the size of the sample of vanillin or whatever you're studying of water. You should have the same mass percent of each element or percentage composition within that compound. And because it's always constant, the percent composition will allow you to identify, to figure out what a mystery substance is if you're not sure what it is to begin with. And like I said, there's two main ways you can calculate the mass percent or the percentage composition as well. You can do that from mass data or from a chemical formula. So let's start off with the example of the percentage composition from mass data. In this case, you do not have a formula. You have an unknown formula. But we put our sample through a machine, and we through a tool in the lab, and we figured out that our sample has 32.69 grams of zinc and 16.03 grams of sulfur. And in our question, we're telling you to calculate the percentage composition. So we're basically saying, what's the percentage of zinc in this compound, and what's the percentage of sulfur in this compound? So our first step is actually to calculate the mass of the compound in total. And even though it's not given to you, since we know the compound contains zinc and sulfur, we know that the mass of the compound, I'm going to put M comp like this, is equal to 32.69 grams plus 16.03 grams. And so we'll do 32.69. You can put it in your calculator. You can do it in your head too, but do it in your calculator to follow along with me, plus 16.03. And we get 48.72 grams. And that's our total mass of the compound. And so our next step is to do the mass percent of each element. So first we'll start with, it doesn't matter which one you start with, I'll start with zinc. Mass percent of zinc is going to be the mass of zinc divided by the mass of the compound times 100%. Almost like figuring out your score on a test or a quiz. So mass of zinc is 32.69 grams divided by the total mass of the compound, 48.72 grams times 100%. So 32.69 divided by our total times 100, and we get 69.09770,115%, or we could say to 4 sig figs, approximately 69.10%. And that is our mass percent of zinc. Now, we're not done finding the entire percent composition. To find the entire percent composition, you have to find the mass percent of each element. So next, we'll do the same thing for sulfur, except it's the mass of sulfur over the mass of the compound. And sulfur is 16.03 grams divided by our 48.72 grams times 100%. And we get, so now you could have done, oops, I think I put 69 there. I made that mistake before. I meant to say 67. Let's just double check that. Sometimes I make little errors here. So 32.69 divided by 48.72. And is it 67? 67. There you go. 67.10%. Okay. Now back to this one. So 16.03 divided by 48.72 times 100. And I get 32.90229885%, or to 4 sig figs, 32.90%. And what you'll notice is that if you were to add these two together, you would get, well, 100%. If you get larger or smaller, if you get over 100 or lower than 100, significantly higher or lower, then you probably made a mistake. So just double check. It's okay if you're off by a few decimal places sometimes, but really being as close to 100 is the best option here. Now, you could have done, some students sometimes ask, couldn't I have just done 100 minus 67.1 after? And you could have, definitely, to find your sulfur, because there's only two elements there. That would have worked out, but just make sure, the reason I did these steps, the long steps twice, essentially, is because, if I made a mistake in this first one, then my mistake carries through here. So that way, by doing both twice, it allows me to double check my work at the same time, while making sure I understand the concept. So this is the percentage composition of this compound, which contains zinc and sulfur. It's made up of 67.1% zinc and 32.9% sulfur. The mass percent of zinc is this percentage over here, and the mass percent of sulfur is this percentage over here. And we were able to do that from mass data. Now, sometimes you don't have mass data, but you have a formula. So let's go back up to the top here for a second. Let's start off with a simple example. Let's calculate the mass percent of nitrogen in ammonium nitrate. So here I'm not asking you for the percentage composition. If I were asking you for the percentage composition, you'd have to do the mass percent of the nitrogens, the hydrogens, and the oxygen. But here I just want to know specifically for nitrogen. Now you'll notice that there's no mass data given. There's no numbers. It's kind of scary. So what I need to do is I need to get numbers from somewhere. And here's a fancy way to do it when you have a formula. The mass percent of an element can be equal to the molar mass of that element in the compound over the total molar mass of the compound times 100%. So if you don't have mass data, you need to calculate the molar mass of the compound using your periodic table. So molar mass of NH4, NO3, and that's from our periodic table. And so you can calculate along with me. So just in case you forgot where to get data from the periodic table, you go to your calendar over here, just go up to your periodic table over here, click on that, and all the molar mass data is there, right? So you can see, for example, that nitrogen is 14.01, oxygen is 16.00. So that's where you get your mass data from. Make sure that you do calculate this properly. I'm not going to do the full steps because that was in a previous lesson, but if I were to do this, I would get for nitrogen's 28.02 plus my hydrogen's 14.04 plus my oxygen 48. And I get 80.06 grams per mole. Now, I want to find the mass percent of nitrogen. And that's going to be equal to 2 times the molar mass of nitrogen over the molar mass of the entire compound of NH4NO3 times 100%. And the reason it's 2 times the molar mass of nitrogen is because notice there's 2 nitrogens, right? It's because you're trying to figure out the percentage of all the nitrogen in there. You have to take that into consideration. If it was for hydrogens, it would be 4 times the molar mass of hydrogen. If it was for oxygen, it would be 3 times the molar mass of oxygen. But we're dealing with nitrogen, so it's going to be 2 times 14.01 grams per mole over 80.06 grams per mole. And I ran out of room here, but this is all times 100%. So just to carry that out here, so I would get 28.02 grams per mole over 80.06 grams per mole, cross out grams per mole, times 100%, and you get, so 28.02 divided by our total molar mass times 100, we get 34.99875,094%. Or we could, to 4 significant figures, we get about 35.00% nitrogen in the compound. So our third step is simply, therefore, the mass percent of nitrogen is approximately 35%. And so this is the case where you don't have mass data given to you, like we did with the zinc and sulfur example. You just have a formula. And so if you only have a formula, you simply go to your molar mass and use that as your mass data, because the percentage is going to be the same regardless of the size of the sample, right? Regardless of whether you had 1 mole of it or 3 moles of it or 5 moles of it, the percentage will be the same. The amounts may not, but the percentage is still the same at the end of it all. So that was just an example of doing the mass percent of nitrogen specifically. Now, a question might sometimes ask you to do the percent composition of the entire compound. So for example, here I'll put calculate the mass percent of each element in sucrose, which basically means find the mass percent of carbon, hydrogen, and oxygen. So your first step, find the molar mass of the entire compound, because notice there's no mass data given here. So you have to do the molar mass. And just to show you that, I'm doing just 12 carbons, so 12 times 12.01, that's from the periodic table. That is 144.12, and that's in grams per mole. Plus, there's 22 hydrogens times 1.01 from the periodic table. That's 22.22 grams per mole. Plus, there's 11 oxygens. So 11 times 16 from the periodic table, 176.00 grams per mole. And the reason I have 2 decimal places is because the molar masses have 2 decimal places in the periodic table, so I keep it to that. And when I add them, there's still going to be 2 decimal places because it's the smallest number of decimal places. So I get 176 plus 144.12 plus 22.22, and I get 342.34 grams per mole. So this is like the total mass of my compound if I had a mole of it. And now I want to find the mass percent of each element. So for carbon, for example, it's 12 times the molar mass of carbon, because there's 12 carbons, divided by the molar mass of my compound of C12H22O11 times 100%. And if I were to write that with numbers, I would get 144.12 grams per mole divided by the 342.34 grams per mole. Cancel grams per mole out because it's the same unit in top and bottom, times 100%. And I get 144.12 divided by that answer, times 100, 42.09849857%. Or I can do, let's see, about 5 sig figs, because that's what there is in my division here, 5 and 5 on top. So I can say 42 point, if I round up here, 42.100%. I just want to make sure that is correct. Let me just see. So 140, I had 12 times 12.01. I'm just rechecking my molar masses here, plus 22.22, plus my 176, 342.34, good. And then I do 12 times 12.01 divided by that answer times 100, and I get about 42.100%. Just because I want to have 5 sig figs there. I can do the same thing for the mass percent of hydrogen. I'm not going to rewrite everything here. Well, I will actually, just to make sure I'm thorough. So mass percent of hydrogen is going to be 4 times the molar mass of hydrogen over the molar mass of the sucrose times 100%, which is going to be equal to the 4.04 grams per mole over 342.34 grams per mole. Cancel that out, times 100%. So 4.04 divided by 342.34 times 100. And I get about 1.180113338%. And if you want to do that to the correct number of sig figs, so we had 3 sig figs, about 1.18% for hydrogen. And then lastly, for oxygen, we had 11 oxygen, so 11 times the molar mass of 1 oxygen over the molar mass of the sucrose, C12H22O11, times 100%, which is 176.00 grams per mole, divided by 342.34 grams per mole. Cancel out grams per mole, times 100%. We get, so let's retry that, 176 divided by 342.34 times 100, 51.41087%, or to 5 sig figs, so up to here, 51.411%. And that would be the mass percent of oxygen, hydrogen, and carbon in sucrose, which is together called the percent composition. If I were to add all these up, so plus 42.100 plus 1.18, I get, I think I might have made a mistake. Let me double check. So 42.1 plus 51.411 plus 1.18. My percentages did not add up to 100. So I made a mistake somewhere here. And I see where the mistake is. For some reason, I said there were 4 hydrogens. And if you were confused and yelling, stop, 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 that's good. That means you were paying attention. So notice that I checked my work and I noticed there was an error there. I did it on purpose. No, I didn't. I wish I did. There are 22 hydrogens in my compound, not 4. So 22 times the molar mass of hydrogen. And we get 22.22 grams per mole there. So let's redo that. 22.22 divided by 342.34 times 100. And this makes more sense now. 6.49, 0.623357. 0.623357%, or to 4 sig figs, 6.491%. Now, if we add these up, let's hope that works. Plus 51.411 plus 42.100, we get about 100%. So our rounding might make us go a little bit over by a couple decimal place, but by a few decimal places down. But overall, this is pretty close to 100%. So we are on the right path. Much better than we had before. Before I was off by 6% or so, or 5 point something percentage. So this is much better. So that's why it's always important to check that final answer by seeing that everything adds up to 100. And it worked out beautifully there because I was able to spot my error and fix it pretty quickly when I noticed that I didn't have enough hydrogens there. So make sure you do practice by redoing these problems yourself if you weren't too sure on how to approach them. There's also some great practice problems to do right over here, number 1 and number 2, before you go on to the worksheets. And there's also an exit ticket for you to try out on Brightspace if you'd like. And you can see the answers for these problems in the slide deck that we were looking at earlier.